Welcome to Gen.Struct.2 Lateral Forces, lesson number 1 quiz, question number 8. And it asks, I can't see the whole entire thing. It says, compared to a simple beam, a continuous beam has, and that's A, B, C, or D. And before I look at these answers, I'll go over a simple beam compared to a continuous beam. Let's go over those real quick. Simple beam is similar to this, and actually a true simple beam will have a pin and then a roller, and this is how I've always shown a roller. But in the end, a determinate beam will have a reaction right there, a reaction right there, and then we'll have either a reaction on this side or a reaction on this side. But in this side we have a pin, so that'll have a horizontal reaction and a vertical reaction. But these don't have to be horizontal and vertical. I hope you know what I mean when I say that. It just needs to resist two perpendicular ways. Alright, so that's a simple beam. It is going to deflect like so. It's going to have positive shear only. If we want to do a quick, that's your deflection. And you can actually do a deflection diagram as well, and you'll see in later, if you continue on in structural, you'll see that the deflection has a lot to do with the moment as well. So the same way we kind of integrate and we use calculus to figure out what your shear and moment diagrams are, a simple form of calculus. You also do the same thing to get to your deflection and your rotation. And I'm not going to get into that any further. That's all I'm going to say, because that will get confusing, and I don't wish to do that. But let's assume, let's go to purple real quick, and you have a uniform distributed load is what we typically will do. And you'll see a lot of these in building structures as a uniform distributed load. In bridge structures, you'll see this uniform distributed load for a, your dead load. It will typically look similar to that. You'll have a lane load possibly, and then sometimes you'll have trucks, and trucks will be point loads that are a certain distance apart and a certain weight. But let's go ahead and move on. Let's say we have a uniform distributed load. Hopefully you know by now that your shear diagram will look like this, and your moment diagram will look like this. And obviously I don't have the best drawing tools to use right here, because it's just not the easiest to draw with, but there you go. And right at this point, where your shear is 0, that's your point of maximum moment. Alright, I've kind of gotten away from this. But as you can see, you only have positive moment. What is a continuous beam? A continuous beam will typically be indeterminate, and what you'll see is you will have we're going to do the same shear and moment diagram down here. And I'm sorry I'm switching up colors. I probably should have got it back and used the same colors, but I'm not going to. We have the same loading, uniform distributed load, and it's going to look somewhat, your positive moment is going to be up here, and then it's going to dip down to your negative moment over that center support. Then it's going to come back and go right back there. And it will be, if it's a uniform distributed load, it will be positive here. Well, actually, let me just do this. Positive, negative, positive. And you could figure out your what is this called? Shear distribution as well, but I'm not going to get into that right now. If you wish to do that, figure out that, you can go ahead. You could either come from here and go up there, or come from your loading and go down. But this is typically what it will look like for moment. And let's go ahead and take a look at so this is all positive. Look at the questions. I'm assuming we'll have something to do with maybe a negative moment, or the positive moments being less than this positive moment. Oh, but it is a little bit confusing, but I'll try to work it through. Let's go ahead and go to the questions. And it says a continuous beam has greater positive moment, and that will be no. That's incorrect. So it will have less moment. Let's say this entire thing is 10 foot. The L is 10 foot. This is L. 10 foot, and this is 10 foot. So we're talking about the same span, but you can look at it, and if you're looking right here, just looking at this, and you load it the same, this will actually be smaller positive moment than your single span. And that's the beauty of using these continuous beams, is it actually helps out a lot with deflection. You'll find that out later. And it does help out quite a bit with moment as well. So if you need to, for instance, if you analyze a roof truss, and I was doing this the other day, where it had a support here, obviously a support down here, a support here, a support here, and a support here. It's a pretty long truss, let's say, or not truss, but, and this was, you know, braced down here, this was braced down there, braced down there. So what you can assume is, okay, this is all braced. What I originally did was say, hey, let's look at this conservatively, because I knew this moment for a simple span is actually going to be less than if you assume continuous. And they have, if you go to your steel manual, you can look up, they'll have these equations where you, in terms of WL squared, you can multiply it by some constant, and it will give you the max positive moments at each, you know, interior or negative over the negative moment. They'll have, like, for instance, this is, I'm guessing, 0.078. This may be completely and utterly off, and this is going to be plus 0.006, I'm guessing. And this will be 0.06 as well. So all you do is you do your uniform distributed load. This is for uniform distributed loads. They also have like a point loads at quarter points and point loads at, I think, half points. Once again, don't take my word for it. Go to Steel Manual, look around, and you'll find that. Sorry, I don't have it with me right now, or I would tell you what page on a certain Steel Manual. All right. So, as I said, this is kind of WL squared. This is 1.0. Or, yeah. And this is going to be probably more closer to 0.60, 0.60. So it does cut down on your, in 0. There you go, 0.78, let's say. It's not going to be 0.06 of what this would be. So that's what you're looking at. This moment will be less than this moment for an equal span. If you have 10 foot, this moment will be less. That's what I was trying to get to, and I'm kind of beating it. All right. So what I did was I said, okay, well, let's look at a max span here to here. Let's assume simple span, because that will be conservative. And let's take your load. And what you start with is you have a horizontal load, snow load, let's say. And it's a gravity load. Then you have to figure what is the perpendicular piece of that, and then figure out what your moment and bending is. And I was finding that I was getting way too much deflection. And then what I did was go back and say, okay, well, let's assume 2 spans. And it's continuous over those 2 spans, so it'll more look like that, your deflection. Not your deflection, but your moment diagram, like we have here. And I found that the deflection was getting a lot better. And if I would have done it even more to 3, I would have seen that it would have helped out even more. Usually if you get to, the more you go, I can't say if you have 100 spans that are exactly the same that it will help. You get to about 5, I believe, and it starts to even out. Everything over 5, you just assume 5. And then 4 is not much different than 5 equal spans. All right. Hope that was not too confusing. So in the end, let's go over A. A, it says greater positive moment, and we said no, that's untrue. It will have less positive moment for the same span. 10 foot, 10 foot, it will have less moment. All right, B is less shear, and that is incorrect. And I should actually do this, and maybe if I have time at the end, I'll do it real quick. Let's keep on going, but that's incorrect. More deflection. As I said earlier, it will actually have less deflection. The continuous beam will have less deflection. I hope that made sense to you. And once again, you can go into, they have standard equations, or, well, maybe on second thought, I don't think they have standard equations, because since this is indeterminate, it depends on what your cross section is. So what kind of E and I you have. It will be a form of EI. So, but you can figure that out. It will have less deflection. In other words, it will. All right. So there are, if you do have a uniform load, there are equations for that as well, as long as that's standard. And then let's go to D. It says greater negative moment, and that's of course true because your single span doesn't have a negative moment. This is all positive, and this is your only negative part. So yes, it will have greater negative moment. And you can know that it has a positive moment only in the single span because it deflects that smile shape. And I hope that makes sense to you. A smile is indicative to positive moment. And as soon as you start to, and I drew this different than you might want to draw it, but when you come in and draw the deflection of how is this going to deflect, it's going to look like this. And as soon as you get to that, as soon as you get to a point where you would think it's going to start frowning, it's kind of like a point of inflection where you can eyeball it and say, oh, about right here, about right there, and about right there, it's starting to frown. So that's going to be your negative moment region, and the smiling is your positive moment region. That's an easy way to figure it out. Just go in and say, okay, if I was applying these loads, what would this beam, how would it deflect? And that is your negative moment region when it starts to frown, and your positive moment region when it's smiling. And as you can see, it will correlate down here. All right, I will see you on question number 8.